You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. Cloud application security is a central discipline in modern architectures, ensuring that software remains trustworthy across its entire lifecycle. The purpose of Domain 4 is to provide a body of practices that address security from the earliest design stages through deployment and ongoing operations in the cloud. Applications today are not monolithic binaries running in static environments. They are dynamic, distributed, and composed of multiple services, frameworks, and third-party dependencies. This complexity increases attack surfaces, making security a continuous responsibility. Securing applications in the cloud involves embedding safeguards at every layer, requirements gathering, threat modeling, coding practices, deployment pipelines, and runtime defenses. For learners, mastering this domain means understanding that application security is not a point-in-time check, but an integrated, ongoing practice that unites developers, operations, and security teams to deliver resilient, auditable, and compliant systems. The scope of Domain 4 spans every stage of cloud-native application delivery, from defining secure requirements and designing resilient architectures, to coding defensively, testing thoroughly, deploying with controls, and maintaining observability in operations. Each stage must address both technical risks and business context. For example, secure requirements define encryption needs or regulatory obligations early, while deployment controls enforce artifact signing and secrets management. This holistic scope ensures that security is not bolted on after development, but woven into the lifecycle. In cloud settings, where infrastructure and applications evolve rapidly, an integrated approach is essential. Application security must scale with the speed of delivery, embedding governance and protection in automated pipelines rather than relying on manual gates. A secure software development lifecycle, or SDLC, integrates security activities throughout the planning, design, implementation, testing, deployment, and maintenance phases. Instead of treating security as an afterthought, SDLC practices shift left, embedding threat analysis and code review alongside functional requirements. For instance, security stories may be added to agile backlogs, and code commits may be scanned for vulnerabilities before merging. SDLC also ensures that maintenance includes patching, dependency updates, and ongoing monitoring. By embedding security continuously, SDLC reduces cost and effort, catching flaws early rather than remediating them late in production. It represents the cultural and procedural framework for making application security a shared responsibility across teams. Threat modeling is a structured activity that identifies assets, trust boundaries, attack paths, and mitigations for application components. It asks questions such as, what are we protecting? Who are the adversaries? Where are the weak points? And how can risks be reduced? For example, a threat model of an e-commerce service may highlight the checkout API as a critical trust boundary, requiring input validation and encryption. Threat modeling encourages developers to anticipate adversary behavior, designing defenses proactively rather than reacting after incidents. It also provides a living map of risks that evolves as systems change. In cloud-native architectures, where services are constantly connected and reconfigured, threat modeling helps maintain awareness of where controls are most urgently required. Microservices architecture reshapes application security by decomposing systems into independent, networked services. Each service introduces its own interfaces, versions, and contracts, requiring consistent governance. Security challenges include securing inter-service calls, managing service discovery, and controlling version drift. For example, a payment microservice may require stricter authentication and monitoring than a recommendation engine. The distributed nature of microservices expands the attack surface, but also allows for granular isolation and resilience. Security in this model must include strict API governance, service identity, and runtime protections. By understanding microservices, learners grasp both the opportunities and challenges of modern cloud-native design, where security must operate at scale across many moving parts. Application Programming Interface Security is one of the most critical areas in cloud application security. APIs act as the gateways between microservices, client apps, and external users. Security practices govern authentication, authorization, input validation, and rate limiting at these endpoints. For example, an API may require OAuth tokens for authentication, enforce role-based permissions for access, and throttle requests to prevent denial of service. APIs must also prevent injection, replay, and enumeration attacks. Because APIs expose business logic directly to the Internet, they are frequent targets. Robust API security is thus essential, blending identity controls with traffic governance to ensure that services remain both usable and defensible. Authentication establishes identity, and in cloud settings it must align with federated identity providers and multi-factor options. Secure systems avoid hard-coded credentials and instead rely on standards like SAML, OIDC, or OAuth to integrate with enterprise identity. For example, a SaaS platform may delegate user authentication to a corporate directory, enforcing MFA for privileged actions. Authentication ensures that every request is tied to a valid identity, closing the door to anonymous abuse. In distributed applications, consistent authentication frameworks simplify design and reduce risk. Strong authentication is the first step toward trustworthy application access. Authorization enforces least privilege once authentication is established. Role-based access control assigns users or services into predefined groups, while attribute-based access control makes decisions dynamically based on attributes such as time, location, or device posture. For instance, RBAC may allow only administrators to create new API keys, while ABAC may restrict data export to corporate-managed devices. In cloud applications, authorization ensures that even authenticated identities cannot exceed their intended scope. It transforms identity from a binary check into a granular control, aligning access tightly with business intent. Input validation and output encoding form the classic defensive duo against injection and cross-site scripting attacks. Validating inputs ensures that only expected data formats are processed, rejecting malicious payloads. Encoding outputs ensures that any potentially unsafe content is rendered harmless in the browser or client. For example, rejecting scripts in user comments and escaping outputs prevents stored XSS. Cloud applications, often exposed directly to global traffic, cannot assume benign inputs. Defensive coding practices ensure that user-supplied data is handled safely, preserving both security and reliability. Secrets management is vital in cloud applications, where credentials, tokens, and keys abound. Hard-coding secrets in source code is a critical anti-pattern. Instead, secrets must be stored securely in vaults or key management services, injected into applications at runtime under strict audit trails. For example, an application may fetch database credentials dynamically from a vault using short-lived tokens. Secrets management ensures that sensitive values are both protected and traceable, reducing the risk of leaks in repositories, images, or logs. It reflects the principle that secrets should be dynamic, auditable, and never embedded directly in code or configurations. Cryptography choices determine how applications protect data in transit, at rest, and in use. Best practices require vetted algorithms, proper key lengths, and secure key management. For example, AES 256 for storage, TLS 1.3 for network transport, and hardware-backed key custody for encryption keys. Cryptography must be applied consistently, avoiding pitfalls like weak ciphers or custom algorithms. In cloud applications, cryptography also protects ephemeral and multi-tenant workloads, ensuring confidentiality across shared infrastructure. By aligning cryptographic practice with standards and governance, applications gain robust protection against both interception and tampering. Dependency governance addresses risks from open source and third-party libraries, which often compose the majority of application code. Software composition analysis tools inventory dependencies, track versions, and flag vulnerabilities or license issues. For example, an outdated JSON parser with a known CVE may be flagged during builds. Governance ensures that dependencies are updated promptly, sourced from trusted registries, and monitored for supply chain risk. Without governance, transitive risks multiply silently. With it, applications maintain transparency and resilience across their software bill of materials. Configuration management ensures that application settings are externalized, securely stored, and applied consistently. It prevents insecure defaults and avoids embedding secrets or sensitive parameters in code. For example, toggling debug mode or encryption settings should be handled through controlled configuration, not hard-coded constants. In cloud applications, configuration drift can create vulnerabilities if not managed centrally. Externalized and controlled configurations provide flexibility while maintaining security, ensuring that changes are deliberate, traceable, and reversible. Logging and observability make application behavior visible for detection and forensic purposes. Structured logs, metrics, and distributed traces provide signals of both performance and attack attempts. For example, failed authentication events may reveal brute force attempts, while error metrics may indicate injection testing. Observability ensures that applications are not opaque but transparent, enabling both proactive monitoring and reactive investigation. Without it, even secure designs become blind to exploitation. Logging and observability provide the feedback loops that make application security measurable and actionable. Privacy by design embeds legal and ethical requirements directly into application flows. Principles include data minimization, purpose limitation, and support for data subject rights such as erasure or access. For example, a healthcare application may encrypt patient records, minimize fields collected, and provide interfaces for consent withdrawal. Privacy is not only a compliance obligation but a trust enabler, ensuring that user data is treated responsibly throughout the lifecycle. Embedding it into design prevents costly retrofits and strengthens credibility with users and regulators alike. Resilience patterns support application stability under stress. Techniques include graceful degradation, retries with backoff, and circuit breakers. For example, if a dependency is unavailable, the application may serve cached results rather than fail completely. These patterns ensure that applications can withstand transient failures without collapsing. Resilience aligns closely with security, as denial of service attacks and overloads are often indistinguishable from legitimate stress. By designing resilience into applications, developers preserve both availability and user trust. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Static application security testing provides the first layer of assurance by analyzing source code or bytecode without executing the application. SAST tools scan for insecure patterns such as hard-coded secrets, unsanitized inputs, or improper cryptographic use. Because they run early, often as part of code commits or pull requests, SAST catches flaws before they reach runtime. For example, a scan may flag an unchecked string concatenated into a SQL query, preventing injection vulnerabilities. While SAST can produce false positives, disciplined tuning and developer feedback loops turn it into a proactive safeguard. It aligns with the SDLC principle of shifting security left, embedding analysis at the earliest stage to prevent insecure code from entering the delivery pipeline. Dynamic application security testing complements SAST by probing running applications from the outside. These tools send crafted inputs and analyze responses to uncover vulnerabilities such as cross-site scripting, injection, or authentication bypass. For instance, DAST may detect that an application improperly echoes unsanitized input, enabling XSS. Unlike static scans, DAST tests real runtime behavior, identifying flaws missed in code analysis. However, DAST requires deployed environments and may struggle with complex workflows or modern APIs. Used together with SAST, it provides a balanced view, Static checks catch code-level flaws early, while dynamic tests validate live systems against adversary techniques. Interactive application security testing bridges the gap by instrumenting applications during runtime. IAST tools monitor code execution paths, linking vulnerabilities directly to the lines of code that caused them. For example, if an injection attempt reaches an unsafe query method, IAST highlights the precise path from input to execution. This hybrid approach reduces false positives and provides developers with actionable insights. IAST often integrates into QA or staging environments, providing continuous feedback as applications are exercised. It reflects the principle of layering detection, combining the breadth of DAST with the depth of SAST, producing targeted findings that developers can address quickly and confidently. Software composition analysis focuses on the third-party components that dominate most modern applications. SCA tools inventory open-source libraries and frameworks, identify versions, and cross-reference them with vulnerability databases and license obligations. For instance, an SCA scan may reveal that a widely used logging library has a high-severity CVE, prompting patching or replacement. Because dependencies often represent the majority of application code, SCA provides critical visibility into transitive risks. It also supports compliance, ensuring that license terms are respected. In cloud application security, SCA is indispensable, tying supply chain governance directly into application lifecycles. Runtime application self-protection provides defenses inside the application itself, monitoring for and blocking malicious behavior during execution. RASP instruments the runtime environment, detecting anomalies such as injection attempts or unexpected code execution. For example, if an attacker tries to manipulate a query, RASP may intercept the call and block it. Unlike perimeter defenses, RASP has context from inside the process, enabling precise detection with fewer false positives. It turns applications into active defenders, capable of protecting themselves even when external controls fail. RASP embodies the principle that security must extend into runtime, where attacks manifest most directly. Continuous integration and continuous delivery pipelines are critical for embedding security into modern cloud-native workflows. CI/CD must include security gates that scan code, validate dependencies, enforce policies, and verify signatures before promotion. For example, a pipeline may block deployment if a container image lacks a signed digest or contains critical vulnerabilities. Integrating security into CI/CD ensures that speed does not come at the expense of safety. It operationalizes SDLC principles, making security checks automatic, repeatable, and enforceable at scale. Code signing and provenance controls attest to the integrity and origin of application artifacts. Every build should produce signed outputs, linked to verified sources and processes. For example, a signed container image provides assurance that it was built from the intended source code in an approved pipeline. Provenance metadata documents who built it, when, and with what dependencies. Together, signing and provenance make artifacts tamper-evident and auditable. They protect against supply chain risks, ensuring that only trusted software moves forward into deployment. Serverless applications introduce unique concerns because developers have no access to the underlying infrastructure. Security focuses on event validation, ensuring that only authorized triggers invoke functions. Execution roles must follow least privilege, granting only the minimum permissions needed. Execution timeouts prevent runaway workloads and denial of service. For instance, a serverless payment function might accept only validated events from a trusted API gateway and run with a scoped identity that allows writing only to a transaction ledger. Serverless security emphasizes boundaries, limiting who can invoke, what resources can be touched, and how long execution can last. Containerized applications also demand specialized safeguards. Image integrity must be verified through signatures and scans, ensuring that workloads start only from trusted bases. Namespace isolation separates containers from one another and from the host. Dropping unnecessary runtime capabilities, such as raw socket access, reduces the attack surface. For example, a web container may run without root privileges and with capabilities restricted only to networking and file I/O. By hardening containers at build and runtime, organizations ensure that cloud-native packaging does not become a new attack vector. API reliability and safety require defensive design to protect downstream dependencies. Rate limits, quotas, and circuit breakers prevent abuse and ensure that surges do not overwhelm services. For example, a quota may limit a client to 1,000 requests per hour, while a circuit breaker halts calls to a failing dependency to prevent cascading failures. These controls serve both resilience and security, ensuring that APIs remain available while resisting adversarial use. In cloud-native systems where APIs are ubiquitous, reliability controls are as much a security requirement as a performance one. Secure session management governs how identities persist across interactions. Tokens must have defined lifetimes, enforced rotation, and support revocation when accounts are compromised. Storage of tokens must prevent theft, such as avoiding insecure browser storage or unencrypted logs. For example, access tokens may expire after 15 minutes, with refresh tokens renewing only under controlled conditions. Secure session management ensures that authenticated states remain trustworthy, preventing hijacking or replay. It extends identity protection beyond initial login, sustaining confidence throughout user interactions. Secure headers and transport policies harden application communications at the protocol level. HTTP, strict transport security, enforces encrypted connections, while mutual TLS authenticates both client and server. Content security policy headers restrict how browsers execute scripts, mitigating cross-site scripting. For instance, enforcing HSTS ensures that browsers never downgrade to insecure HTTP, blocking interception attempts. These simple but powerful controls ensure that application traffic remains confidential, authenticated, and resistant to injection at the transport layer. Incident readiness for applications ensures that when breaches occur, response is swift and coordinated. Applications must emit structured logs, maintain evidence sources, and include feature flags or kill switches to disable compromised functionality quickly. Rollback paths allow teams to revert insecure deployments. For example, a kill switch may disable a vulnerable API endpoint until a fix is applied. Readiness ensures that incidents are not met with chaos, but with documented, rehearsed actions. It transforms security from prevention alone into detection and response, acknowledging that even secure systems must prepare for failure. Compliance alignment ties application controls to frameworks such as PCI DSS, HIPAA, or GDPR. Applications must demonstrate that encryption, access control, logging, and privacy measures satisfy regulatory obligations. Evidence may include signed SBOMs, scan results, or audit logs. For example, a financial application must prove that cardholder data is encrypted in transit and at rest, and that logs are retained according to policy. Compliance alignment ensures that application security is not only effective, but defensible under external scrutiny. It integrates security with legal and contractual accountability. For exam purposes, learners should focus on recognizing SDLC activities, API protections, layered testing approaches, and runtime safeguards for cloud-native scenarios. Questions may test familiarity with SAST, DAST, IAST, and SCA, or the ability to evaluate serverless and containerized application concerns. Candidates should also understand secure session management, transport headers, and resilience patterns. The emphasis is on applying integrated practices rather than isolated controls, ensuring that application security scales with cloud-native delivery models. In summary, Domain 4 unites secure design, coding, testing, deployment, and runtime practices into a cohesive discipline of cloud application security. SDLC embeds protection from the start, threat modeling anticipates risks, and API-centric controls defend exposed interfaces. Testing layers and SCA ensure that both custom and third-party code are scrutinized. CI/CD pipelines, provenance, and signing establish trustworthy builds, while runtime safeguards like RASP, session management, and resilience patterns keep services dependable under attack. Compliance and privacy obligations weave accountability into every stage. Together, these practices deliver not just functional applications but trustworthy ones. Secure by design, resilient in operation, and auditable under scrutiny. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.